Okay, we're at 17.2, a microscopic view of current and drift speed. And so let's look at the drawing here, and it ends up that current depends on a few things: the average speed of the charge carriers in the direction of the current, the number of charge carriers per unit volume, and the charge carried by each charge carrier. So here we have delta Q is equal to the number of carriers plus charge per carrier. Well, the number of carriers is number of carriers per unit volume. Well, what is the volume? The volume is this area delta X. So it's a cylindrical, we're imagining a wire. So delta X is how far it's drifted, and the area is basically the area of that circle. So that gives you a volume. So the volume is A delta X, and N is the number of charge carriers per volume, times that volume of A delta X times the charge. And that's the overall charge, delta Q. Well, X, distance equals rate times times. Delta X is equal to VD delta T, where VD here is the drift velocity. We'll explain that in a little bit. The drift velocity times delta T. So Q, substituting V sub D delta T into the above equation, we get delta Q, big delta Q equals to NA drift delta T times Q. So the limit as delta I is equal to the limit as delta T goes to 0 of delta Q divided by delta T. So you put delta T in the denominator with what's defined as delta Q above, you end up with NQ V drift times A. So it's the number of charge carriers times the charge per carrier times the drift velocity times the area. That's what current is. We'll stick with the previous definition, coulombs per second, but this is the microscopic view. Now, people think, or maybe not, maybe they don't think, maybe they don't even think about it, but you can turn on a light switch and you think of these electrons, zoom, going to the light bulb. That's not how it happens. When you turn on the light switch, the electric field travels at the speed of light, but the electrons just kind of drift past. And this is kind of an image. Although the electrons move with average velocity v sub d, that's the drift velocity, collisions with atoms cause sharp momentary changes of direction. So if there were no electric field, these electrons would just probably based on the temperature, they would just be kind of bouncing around, in general, staying in the same area. You put an electric field, as shown here, the electric field is to the left, they start drifting to the right. They'll go back a little bit, after bouncing around some of the other atoms in the material. But their overall velocity is opposite the electric field. And that's what it looks like. I was looking for a little simulation. I think in the 2426, Physics 2426, that book provides a little simulation. I couldn't find it since I don't have a web assigned for that. I'm not currently a user of 2426. They show a little simulation. It's just important to know that the electrons don't speed with the speed of light, or even, they're just not very fast. It just kind of drifts to the side. We'll do a homework example. I don't remember if I've assigned a homework. I probably have. And I think that's it basically so the basic idea here is just not to think of electrons moving very, very fast. They do drift. They just kind of slowly drift. The electric field is set up right away, but in response to that electric field, the electrons just kind of move in the direction opposite of the electric field. All right, that's it for this section, 7.2. Next, we'll do 17.3, current and voltage measurements in circuits. You've already done the voltage measurements in the lab today, so we'll, well, by the time you view this, it'll be yesterday. Um, so you know a little bit about voltage measurements. And I lost my cursor. There it is.